Okay, let's dive right into this explainer. We're tackling one of the absolute most mind-bending mysteries in astrophysics. How do we observe things in the universe that emit literally zero light? I mean, it sounds like an impossible premise, right? How do you look at something that's totally invisible? Well, it turns out the universe actually provided us with its very own built-in magnifying glass, and today we're going to figure out exactly how it works. You know, when we look up at the night sky, our standard telescopes are really only catching the luminous parts of the universe. We're seeing the stars, glowing gas clouds, brilliant galaxies, the flashy stuff. But the truth is, the vast majority of the cosmos is entirely hidden from us. We're talking about distant, freezing cold exoplanets and that massive, invisible scaffolding of the universe we call dark matter. So the big question we're answering today is simply, how do we map what we literally can't see?
The secret is a phenomenon called gravitational lensing. Basically, this happens when a massive body, like a star or a whole galaxy, creates such a ridiculously strong gravitational field that it actually distorts and magnifies the light from a distant object behind it. Think of it exactly like a giant cosmic magnifying glass. This was actually a core prediction of Albert Einstein's theory of general relativity. It proves that mass literally curves the fabric of space-time itself, and light just follows that curve.
Here's our roadmap for today. First, the cosmic magnifying glass. Second, the 3 types of lensing. Third, spotting hidden exoplanets. Fourth, uncovering dark matter. And finally, the future of lensing.
Section 1. The cosmic magnifying glass. Einstein's prediction.
Now, check out how perfectly the path of light behaves here. You've got light from a distant, white-blue background galaxy traveling all the way toward Earth. But right in the middle, there's a massive foreground galaxy cluster. As those light rays approach that massive cluster, its intense gravity literally curves the path of the light. So by the time those rays finally reach our telescopes, they've been bent, they've been magnified, and this warping effect lets us see that distant background galaxy, sometimes as stretched out arcs or even multiple mirror images, which we would absolutely never be able to see otherwise.
Section 2. 3 types of lensing. Categorizing the effects.
To really wrap our heads around this, we can break lensing down into 3 distinct types. First up is strong lensing. This is the extreme stuff. It actually produces multiple images of the exact same background object, like the famous Einstein's cross. We use this to study highly magnified, incredibly distant galaxies. Next is weak lensing. This one doesn't create multiple images. Instead, it subtly stretches or deforms the shapes of background galaxies. It is the ultimate tool for mapping large-scale, invisible dark matter structures. And finally, we have microlensing. Here you don't get any visual distortion of shape. You just see a temporary, periodic brightening of a star. And as we'll see in a second, this is our absolute secret weapon for finding small planets.
Section 3. Spotting hidden exoplanets. Using microlensing.
So, when you compare microlensing to standard planet hunting methods, like looking for planetary transits, a pretty stark contrast emerges. Most other methods are really only effective at finding planets maybe a few hundred light years away from Earth. But microlensing, it probes the entire galactic population. Here's how it works. When a star passes in front of a background star, that background star brightens. But if the foreground star has a planet orbiting it, that planet acts as a mini-lens, creating a tiny secondary blip in the brightness. It's an incredibly unique signature. It lets us find planets in the freezing outer edges of their star's habitable zone. It even lets us spot tiny Earth-mass planets and totally rogue free-floating planets thousands of light years away that would be completely invisible otherwise. To put that into perspective, by October 2018, we had already discovered at least 80 of these elusive, cold planets using this specific microlensing trick. It's just an amazing testament to letting gravity do the heavy lifting for us. Literally, just by letting things be massive.
Section 4. Uncovering dark matter. Mapping the cosmic web.
Now, for decades, astrophysicists have worked with this cosmic web theory. The idea is that the universe is basically structured like a giant spider web, where incredibly dense galaxy clusters are linked together by these vast thread-like filaments of dark matter. But there was a huge historical roadblock. Proving this invisible skeleton actually existed was ridiculously frustrating. Scientists knew more than half of all matter should be hiding in these filaments, but early attempts to detect them were just plagued by low signal-to-noise ratios and frustrating false positives. It was essentially a cosmic detective story that was missing its smoking gun.
But then we got the solution, a direct mass reconstruction of the Able 22 and 223 supercluster system. Those blue topographical contours represent surface mass density, and they were mapped out entirely by weak gravitational lensing.
By measuring the tiny, sheared distortions of over 40,000 background galaxies, researchers didn't just guess where the mass was, they directly mapped it out. And if you look right there in the middle, you can see a distinct mass bridge. That is a dark matter filament, physically connecting the two massive clusters.
And this wasn't just some faint, maybe it's there signal either. That mass bridge was detected at a staggering 4.1 sigma significance level. In the physics world, that level of statistical significance means we can be incredibly confident that this dark matter filament is a real, physical structure, not just a glitch or background noise.
But of course, the researchers had to be absolutely certain. They had to prove this mass bridge wasn't simply the outer edges of the two cluster halos awkwardly overlapping. To do that, they ran highly complex statistical models, like this probability grid right here. By plotting the sizes of the clusters against the strength of the filament, they ran tens of thousands of simulated variations just to see if a model without a filament could ever explain the gravitational signatures we were actually observing.
So, the verdict? All those simulations made it crystal clear. The actual mass density exceeded the clusters-only model's 98.5% of the time. The data practically demanded the presence of extra mass between those clusters. The dark matter filament is completely real, and it contains a mass comparable to an entirely separate galaxy cluster. On top of that, by bringing in X-ray data, they figured out that the hot gas fraction in this filament has an upper limit of just 0.09. That means the vast majority of this gigantic bridge is purely invisible dark matter, and we only mapped it because it bent the light of the galaxies behind it.
Section 5. The future of lensing. Enter the next-gen telescopes.
Okay, so everything we've talked about so far, it's about to be totally supercharged by NASA's upcoming Nancy Grace Roman Space Telescope, which is set to operate around 2027. Roman is going to run a high-latitude, wide-area survey. To really grasp the leap in technology here, get this. Every single image Roman takes will be 200 times larger than an infrared snapshot from the Hubble Space Telescope. Because of that gigantic field of view, Roman is expected to flag an astonishing 160,000 lensed galaxies. And from that massive dataset, scientists think they'll isolate about 500 pristine, strong lenses that are perfectly tailored for mapping dark matter. We're literally moving from a tiny sample size of a few dozen good lenses to hundreds and thousands.
And as Tansu Dalen from Washington University points out, it isn't just about getting more lenses. Roman's insanely sharp, high-resolution images are going to let us find gravitational lenses that appear much smaller on the sky. This is a game changer. It means we won't just be restricted to mapping giant filaments between huge galaxy clusters, we'll actually be able to map dark matter distributions on incredibly fine scales right within individual foreground galaxies.
The best part? Roman isn't going at this alone. Once Roman identifies these hundreds of thousands of lensed galaxies, we can point telescopes like the James Webb Space Telescope, the JWST, exactly at them. JWST can then study those highly magnified background sources in unbelievable detail, picking up objects fainter and farther away than anyone thought possible. By teaming up Roman's wide-net surveys with JWST's precision deep dives, we are for sure entering a golden age of testing Einstein's general relativity.
Which leaves us with a pretty staggering thought to wrap up this explainer. I mean, if simply letting gravity do its thing has already allowed us to pinpoint tiny, freezing planets thousands of light years away and literally map out the invisible dark matter skeleton of the cosmos, what totally unimaginable hidden structures are just waiting to be discovered in the next 160,000 cosmic lenses? The universe is absolutely waiting to show us its secrets. We just have to remember how to look through the glass.